When you look at the night sky, you see light that set out billions of years ago. The glow of the stars, the rotation of the galaxies, the dance of the planets. But all of this had a beginning. And at this exact point, we face the biggest question that challenges our minds. What was there before the beginning? Modern science tells us that the universe began about 13.8 billion years ago with a massive event we call the Big Bang. It explains that from an infinitely small point, from a singularity, all matter, energy, space, and time burst outward. According to this theory, the universe began to exist in an instant. But the human mind is curious by nature. It asks, but what about before? What was there before that first spark? This question is not just a philosophical curiosity, it is a critical key to understanding reality itself. Because if everything has a beginning, we cannot truly understand the nature of existence without understanding what came before that beginning. On this journey, we will take you to the threshold of the most mysterious door of science. If you're ready to explore what came before the Big Bang, if you have subscribed, we can begin. The story begins in the late 1920s. Georges Lemaitre, a Belgian priest and physicist, proposed an idea that no one had dared to think about until then. The universe is expanding. And if you rewind time, the entire universe compresses into a single point. When the observations of Edwin Hubble confirmed this idea, the scientific world was shaken. Galaxies were moving away from each other. This meant that there had been an explosion in the universe. The Big Bang Theory proposes that the universe began 13.8 billion years ago from an infinitely dense and infinitely hot state. In those first moments, the universe was smaller than atoms at an unbelievably tiny scale called the Planck length. The temperature was beyond words, exceeding 10 to the 32 Kelvin. The first 10 to the minus 43 seconds are known as the Planck time. And here, the laws of physics as we know them collapse. Quantum mechanics and general relativity mix together, becoming meaningless. But afterward, the universe begins to expand rapidly. Within just fractions of the first second, a process called inflation occurs. The universe grows trillions of times in the blink of an eye. This early universe was a cauldron filled with pure energy. Particles were constantly forming and disappearing. Quarks, gluons, photons, matter and antimatter kept colliding, annihilating each other. But somehow, matter won. Without this asymmetry, nothing would exist today. Within the first 3 minutes, nuclear fusion began. Hydrogen atoms merged to form helium. The first elements of the universe were born in this firestorm. Then, about 380,000 years later, the universe cooled enough for the first atoms to form. Light could finally move freely. The echo of this moment can still be observed today as the cosmic microwave background radiation. Millions of years passed and gravity began to do its work. Clouds of matter came together. The first stars began to shine. Galaxies took shape. And eventually, billions of years later, on a small blue planet, consciousness emerged and began to question its own origin. This story is breathtaking, but it doesn't end here, because we still haven't answered the most fundamental question. What was there before all of this began? Right at this point, your mind feels like it hits a wall. The Big Bang Theory is wonderful, magnificent, full of evidence. But the idea of a universe starting from a singularity doesn't really explain anything. It only defines the starting point. Think about it. If the entire universe is in a single point, what is outside that point? If time began with the Big Bang, can something like a before even exist? If there is no time, how can cause and effect work? These questions can drive you crazy. Some physicists say, the question of what came before the Big Bang is meaningless because time itself began with the Big Bang. There is no concept of before. This seems logical. Stephen Hawking made a famous analogy about this. Asking what came before the Big Bang is like asking what is north of the North Pole. It is a meaningless question. But the human mind struggles to accept this. Everything must have a cause, right? If the universe came into existence, something must have caused it, or at least there must have been a previous state. This way of thinking leads us down two paths. Either we accept that the universe suddenly appeared out of nothing, without a cause, which contradicts the basic principles of the scientific method, or we accept that something existed before the Big Bang, that there was a before we simply do not yet understand. Modern physics has begun to choose the second path, and the theories that have emerged rival even science fiction. The truth is, this question is not only scientific, but also existential. To understand who we are, why we are here, we need to know where we came from. And that means not just where we came from as a species, but where we came from as a universe. Physicists, mathematicians, and cosmologists trying to answer this question have developed new theories. Some seem crazy, some almost mystical, but they all try to reach the same goal: to lift the curtain on what came before the Big Bang. What is time? This simple seeming question is actually just one of the most complex problems in cosmology. In daily life, time seems simple, like a river flowing from the past to the future. But Einstein's theory of relativity taught us that time is something far stranger. According to Einstein, time is not absolute, but relative. It cannot be thought of separately from space. We live inside a four-dimensional fabric called space-time, and this fabric is bent and distorted by matter and energy. Gravity is actually the curvature of space-time. As we approach the Big Bang, the curvature of space-time becomes infinite. Mathematics collapses. A singularity forms, and right here, time itself loses its meaning. But some physicists propose that time may not actually have a beginning. According to Roger Penrose's cyclical cosmology theory, the Big Bang is actually part of a cycle. Our universe was born from the death of a previous universe, and when our universe dies, a new universe will be born, an infinite cycle. According to Penrose, in the very distant future of the universe, all black holes will evaporate, all stars will fade, and only photons will remain. This state looks very much like a singularity, just like before the Big Bang. And perhaps this state triggers a new Big Bang. In this theory, time is infinite. There is no beginning, no end. There are only endless cycles. This idea resembles the concepts of eternal cycles in Eastern philosophy. But Penrose's theory is not just philosophical, it has mathematical foundations. Another approach is Julian Barber's timeless universe theory. According to Barber, time is an illusion. In reality, every moment exists separately, with no real connection between them. This means a universe that is a collection of nows. Each moment is complete and independent on its own. The ideas of past and future are just illusions created by our consciousness. From this perspective, the question of what came before the Big Bang loses its meaning, because there is no such thing as before or after. There are only different configurations. Some physicists, like Lee Smolin, argue that time is real, but the universe may have changing laws. Perhaps the laws of physics evolve. Perhaps before the Big Bang, there were different laws. This idea leads to the theory of cosmic natural selection. Universes may evolve just like living organisms. Quantum mechanics, the strangest and most successful theory of the 20th century. In the subatomic world, everything works in incredibly strange ways. Particles can exist in more than one place at the same time. Observation can change reality. And most importantly, nothingness is not truly nothing. In quantum mechanics, what we call the vacuum is actually a boiling sea of energy. Virtual particles are constantly appearing and disappearing. This is a fact proven by the Casimir effect, observed in laboratories. Physicists like Lawrence Krauss suggest that our universe may have emerged in exactly this way. As a result of a quantum fluctuation, the universe might have suddenly appeared out of nothing. It sounds crazy, but it is consistent with the laws of quantum mechanics. The idea is this: even in a state where there is nothing, quantum uncertainty exists, and this uncertainty allows energy fluctuations. Heisenberg's uncertainty principle says that for very short periods, energy can be borrowed. If this fluctuation is large enough, it could start a universe. But here is an important question. Is this quantum nothingness really nothing? After all, we are talking about a framework where the laws of quantum mechanics exist. A place with laws cannot truly be nothing, can it? This leads us to a deeper question. Where do the laws of physics come from? Why does quantum mechanics exist? Why does mathematics work? The answers to these questions may lie beyond the limits of science. Alexander Vilenkin proposed the tunneling hypothesis. Quantum tunneling is a known phenomenon. Particles sometimes pass through barriers they shouldn't be able to cross. According to Vilenkin, the universe may have tunneled into existence from nothing. In his mathematics, this seems possible. But again, this nothing is not absolute nothingness. It is a state where potential energy fields and quantum uncertainty exist, not the total absence of existence. Alan Guth's inflation theory expands these ideas. According to inflation, a tiny quantum fluctuation could create a small region trapped in a false vacuum state. This region would expand at an incredible speed, inflation, and as a result, our universe would emerge. All of these theories are mathematically consistent, but they are still speculative because we cannot directly observe what came before the Big Bang. We are only searching for indirect evidence. If a universe can emerge from nothingness, why should there be only one universe? Perhaps there are infinitely many universes. Perhaps ours is just one of them. The multiverse hypothesis has become popular in recent years, but it is not just science fiction. Serious physicists are discussing this idea. The first version comes from Hugh Everett's many worlds interpretation. In quantum mechanics, a particle exists in all possible states at the same time until it is measured. According to Everett, during measurement, the universe splits. A separate universe forms for each possible outcome. This means an infinite number of parallel universes. According to this theory, right now in other universes, there are other versions of you. In some of them, you made different decisions and lived different lives. Every quantum event branches the tree of the universe. Another version comes from inflation theory. If inflation can happen once, it can happen again and again. Perhaps in different regions of space, new universes are constantly forming, each one a mini-universe beginning with its own Big Bang. This is called eternal inflation. In this scenario, our universe is a bubble inside a vast megaverse, and around us there are countless other bubbles, but they cannot communicate because the space between them is expanding too quickly. String theory offers an even wilder version. According to string theory, there are 11 dimensions, 10 of space, 1 of time. We can perceive only 3 spatial dimensions. The other dimensions are extremely small, curled up. But perhaps some universes extend across different dimensions. The idea of brane cosmology suggests that our universe is a membrane floating in a higher dimensional space, and there are other membranes as well. Sometimes these membranes collide, and these collisions create new Big Bangs. According to this theory, our Big Bang was actually the collision of 2 membranes, and before that, these membranes already existed, drifting in higher dimensional space. The multiverse hypothesis has one major problem. It is not testable. If we cannot access other universes, how will we prove they exist? According to some scientists, this brings it closer to philosophy than to science. But its supporters say there could be indirect evidence. For example, certain anomalies in the cosmic microwave background radiation could be traces of collisions with other universes. Or the fact that the physical constants of our universe seem finely tuned might be explained by a multiverse. Because if there are infinite universes, in some of them, the values that allow life would arise by chance. Some ancient civilizations believed that time was cyclical. Everything repeats within endless cycles. Modern physics is rediscovering this old idea. Roger Penrose's conformal cyclic cosmology theory proposes that our universe is part of an infinite cycle. Each cycle is called an eon. Our universe is one eon, but before it, there were other eons, and after it, there will be more. According to Penrose, in the very distant future of the universe, all matter will disperse. Only photons will remain. And for photons, time does not pass because they move at the speed of light. So the universe returns to a state where time does not exist. This state is very similar to the condition before the Big Bang. And Penrose shows, through a mathematical transformation called a conformal transformation, that the end of one eon matches the beginning of the next. In this theory, before our Big Bang, there was another universe, and before that universe's Big Bang, another universe. It goes back infinitely. Penrose claims that there are traces from previous eons in the cosmic microwave background radiation. Some circular patterns may be Hawking points left behind by collisions of supermassive black holes in a previous eon. These claims are controversial. Other scientists say these patterns could be statistical noise. But Penrose's theory is at least testable, which is important for science. There are other cyclical models as well. The ekpyrotic theory of Paul Steinhardt and Neil Turok proposes that two parallel branes collide again and again. Each collision starts a new cycle. This model is based on string theory. In the ekpyrotic model, the name comes from the Greek word ekpyrosis, meaning conflagration or out of fire. The Stoic philosophers of ancient Greece believed the universe was destroyed by fire and reborn. The modern version replaces fire with brane collisions. The appeal of these cyclical models is that they remove the problem of a beginning. If there is an infinite cycle, the question of the first cause disappears. Each cycle comes from the previous one. But this creates another question. Where do the cycles come from? Why do cycles exist? And what happens to the second law of thermodynamics? Doesn't entropy keep increasing? Penrose's answer is interesting. At the beginning of each eon, the universe starts with low entropy. At the end, high entropy. But during the conformal transformation, something like a reset of entropy occurs, because entropy is related to information. And in a world of photons, information is defined differently. To understand what came before the Big Bang, perhaps our most important need is a theory of quantum gravity. Right now, we have two wonderful theories, quantum mechanics and general relativity, but the two do not get along. Quantum mechanics perfectly describes the subatomic world. General relativity explains gravity and the universe beautifully, but when you try to combine them, the mathematics explodes. Infinities appear. In the first moments of the Big Bang, the universe was so small and so dense that both quantum and gravitational effects were important at the same time. To understand this situation, we need a theory of quantum gravity that unifies both. String theory is the most famous candidate. According to string theory, fundamental particles are not points, but vibrating strings, and the different vibration modes of these strings create different particles, including gravity. String theory is mathematically very rich, but it has a problem. It is not testable. The size of strings is so small, the Planck length, that direct observation is impossible, and the theory predicts 10 to the 500 different vacuum states, each with different physical laws. Which one is our universe? No one knows. Loop quantum gravity is an alternative approach. According to this theory, space-time is also quantized, meaning it is granular. At very small scales, space is not continuous but discrete, like a screen made of pixels. According to LQG, the Big Bang is actually a big bounce. The universe does not collapse into infinite smallness. When it reaches a certain minimum size, quantum effects take over and push the universe back into expansion. So before the Big Bang, there was a previous universe, and that universe was collapsing. This model resembles cyclical cosmologies, but the mechanism is different. Here, quantum gravity prevents the singularity. Infinite density cannot form. Physicists like Carlo Rovelli and Abhay Ashtekar believe that LQG may explain what came before the Big Bang. According to the model, as the previous universe collapsed, it shrank to a cosmic atom weighing about 1 gram, with a size 1/1000th of a centimeter. Then, the quantum bounce occurred and a new universe began. Causal dynamical triangulations, or CDT, is another approach. It tries to model quantum effects by dividing space-time into small simplices, higher dimensional shapes similar to triangles. Computer simulations show that CDT produces a 4-dimensional space-time, which is promising. All of these theories are not yet complete, but they all pursue the same goal: to understand the first moments of the Big Bang, and perhaps what came before it. Sometimes, to understand what came before the Big Bang, we need to ask a different question. Why does the universe allow life? The physical constants of our universe are incredibly fine-tuned. For example, if the strength of the electromagnetic force were slightly different, atoms could not form. If the strong nuclear force were a bit different, stars could not burn hydrogen and carbon could not form. If gravity were slightly different, galaxies would not form. If any of these constants were different by even 1% from their current values, the universe would be sterile. Life would be impossible. Even matter itself would not form properly. This observation brings two fundamental questions. Is it a coincidence or a design? The anthropic principle offers a third path. It says, observer selection effect. The reason the universe's parameters are suitable for life is simple. If they were not suitable, we would not be here to observe them. Only in universes that allow life does life emerge and ask, why are things like this? This may sound like circular reasoning, but it makes sense when combined with the multiverse hypothesis. If there are infinitely many universes, each with different physical constants, then in some of them life will appear by chance, and we, naturally, find ourselves in a universe that allows life. This is like a lottery winner saying, "Wow, I'm so lucky." Yes, you are lucky, but millions of people played. Someone had to win. It just happened to be you. The weak anthropic principle says only this: the properties of the universe must be consistent with the existence of observers who observe it. The strong anthropic principle goes further. The universe must be set up to produce life and consciousness. The strong version is controversial. Some say it is a design argument outside of science. Others argue it could be a real physical principle. John Wheeler proposed the idea of a participatory universe. Perhaps consciousness plays a role in collapsing the quantum state of the universe. Perhaps the universe does not fully exist without observers. This idea is consistent with some interpretations of quantum mechanics. Lee Smolin offered a different explanation with the idea of cosmic natural selection. Perhaps universes reproduce in black holes. Each black hole creates a new universe in another space-time, and the constants of the new universe are slightly different from the parent universe, like mutations. Over time, universes that produce more black holes become more common. Stars are needed for black holes to form. Complex chemistry is needed for stars. So, universes with high reproductive success also happen, by chance, to be suitable for life. Natural selection explains the fine-tuning. This idea is speculative, but elegant. It is hard to test, but not impossible. Predictions can be made about black hole universe production. Now let's look at a very different idea. Maybe the universe we live in is a simulation. At first, this idea sounds absurd, but think about it. In the future, a sufficiently advanced civilization could create detailed universe simulations. Simulations at the atomic level, even at the quantum level. And within those simulations, consciousness could emerge. If this is possible, then a question arises. How many real universes are there, and how many simulated ones? The answer is probably one real universe and trillions of simulations. Because once the technology exists, countless simulations can be created. Statistically, the probability that we are living in the real universe is very low. Most likely, we are in one of the simulations. Philosopher Nick Bostrom reduced this argument to three options. Advanced civilizations go extinct before reaching the level where they can run simulations. Advanced civilizations are not interested in running simulations. We are most likely living in a simulation. One of these three must be true, and if you believe the first two options are unlikely, then the third becomes the logical conclusion. This hypothesis offers an interesting answer to the question of before the Big Bang. It is simply what happened when the simulation was started. The before is just a state before the program was launched, the time passing in the simulator's reality. But this only moves the problem one level higher. Where did the simulator's universe come from? And what if that universe is also a simulation, an infinite chain of simulations? Some physicists have looked for clues that we are in a simulation. For example, the Planck length, like the pixel size of nature. Quantum uncertainty. It could be a way to save computational resources, fully calculate only what is observed. But these are not definitive proofs, and testing the simulation hypothesis is very difficult. If the simulators are smart enough, they could make the simulation impossible to detect. This idea can also feel a bit depressing, the idea that we are not real. But think about it. Consciousness inside a simulation is still real consciousness. If you feel, you are real, regardless of whether you are simulated. Descartes' argument, "I think, therefore I am," still holds. And perhaps being in a simulation explains the purpose of the universe. Maybe the creators made us to understand how consciousness emerges and how the universe works, a scientific experiment. Another idea that has become popular in recent years, our universe might be a hologram. You know, holography, a three-dimensional image encoded on a two-dimensional surface. The holographic principle suggests something similar. Our three-dimensional universe may actually be information encoded on a two-dimensional surface. This sounds crazy, but it has serious physical foundations. The idea came from the work of Jacob Bekenstein and Stephen Hawking on black holes. The entropy of a black hole, the amount of information it contains, depends not on its volume, but on its surface area. This is very strange. Normally, the information inside a volume should be proportional to the volume. But for black holes, it is as if all the information is encoded on the surface of the event horizon. The volume becomes an illusion. Gerard Tufte and Leonard Susskind generalized this idea. Maybe the whole universe works this way. Maybe our three-dimensional reality is the hologram of information encoded on a two-dimensional surface at a very distant boundary. The ADS/CFT correspondence, coming from string theory, supports this idea. It shows that, under certain conditions, a higher dimensional universe with gravity and a lower dimensional theory without gravity can be mathematically equivalent. If the holographic principle is correct, we can look at the Big Bang differently. Maybe before, there was a different state in the boundary theory. The Big Bang could be the holographic projection of an event on the boundary. This raises deep questions about the true nature of our universe. Is three-dimensional space real, or is the information on the two-dimensional boundary the real thing? Which one is fundamental? The answer, both are equally real. They are different descriptions of the same reality, like a map of a mountain and the mountain itself. One is a representation of the other, but both exist. The holographic principle is also connected to quantum information theory. Information may be the fundamental building block of the universe. Matter and energy may emerge from information. This perspective changes the question, what existed before the Big Bang, into what existed on the boundary. And maybe the boundary is not temporal. Maybe it is spatial. Then the concept of before takes on a completely different meaning. Now let's enter a very speculative but interesting area, the role of consciousness. One of the strangest features of quantum mechanics is the measurement problem. Before a quantum system is measured, it exists in all possible states at the same time. When it is measured, it collapses into one state. But what exactly does measurement mean? At what point does the collapse happen? According to some interpretations, a conscious observer is required. That is, without consciousness, the universe is not in a definite state. If this is true, what was happening in the first moments of the universe when there was no consciousness? Was the universe uncertain because it was unobserved? John Wheeler's delayed choice experiments suggest an even stranger possibility. Present observations may affect events in the past. At the quantum level, cause and effect may be two-way. Wheeler proposed the idea of the participatory anthropic principle. Perhaps consciousness is necessary for the existence of the universe. The universe creates beings that can observe it, and this observation, going backward, makes the entire history of the universe real. This is very speculative, but some quantum cosmology models use similar ideas. The Wheeler-DeWitt equation tries to describe the entire universe with a single quantum wave function. In this equation, there is no time parameter. That means the universe is not something that expands in time, but simply something that exists. From this perspective, the Big Bang is not an event that happened in the past. It is just an aspect of the universe's quantum state. There is no such thing as before, because time is an internal property of the universe's quantum state. Roger Penrose and Stuart Hameroff developed the orchestrated objective reduction, ORC-OR, theory, which proposes that consciousness arises from quantum effects. If consciousness is quantum, perhaps it has a deeper connection with the quantum structure of the universe. Most physicists consider these ideas very speculative, but they are not completely ignored, because the relationship between consciousness and quantum mechanics is still an open question. Perhaps to understand what came before the Big Bang, we must understand the nature of consciousness. Maybe the two are connected. Maybe the universe exists to experience itself. Max Tegmark has a radical idea. The universe is mathematics, not just something that resembles mathematics, literally mathematics. According to this idea, which he calls the mathematical universe hypothesis, physical reality and mathematical structure are the same thing. The universe is a mathematical object. This sounds crazy, but think about it. The laws of physics are mathematical. Everything is described with equations. Atoms, galaxies, black holes, all of them are mathematics. But what if mathematics is not just a tool of description, but reality itself? According to Tegmark, all mathematically consistent structures, in some sense, exist. Our universe corresponds to a particular mathematical structure, but other structures also exist, meaning other universes. This is the most radical multiverse hypothesis, not just universes with different physical constants, universes with completely different mathematical laws. In some, space is not three-dimensional, but 17-dimensional. In some, time has two dimensions. In some, gravity decreases with 1 over r cubed, not with 1 over r squared. From this perspective, the question, what existed before the Big Bang, becomes meaningless, because our universe is a mathematical structure defined with time. Time itself is part of the structure. Outside the structure, there is no time. But this creates a deeper question. Why does mathematics exist? Why does mathematical consistency mean existence? Tegmark's answer, because it cannot be otherwise. Inconsistent things, by definition, cannot exist. Consistent things, by definition, exist in some sense. This is a kind of Platonism. Plato said that ideal forms are real, and the physical world is just shadows. Tegmark takes this to the extreme. Only the forms are real. There is no such thing as shadows. This idea makes many philosophers and physicists uncomfortable because it seems not to explain conscious experience. Mathematics is third-person knowledge, but consciousness is first-person experience. Can seeing red be reduced to mathematics? But maybe it can. Maybe consciousness is also a mathematical structure, very complex, but still mathematics. Maybe seeing red is the subjective side of a particular information processing pattern. Leibniz's famous question, why is there something rather than nothing? This is perhaps the most fundamental of all questions, and it is directly related to the topic of what came before the Big Bang. It seems logically possible that there could have been nothing. The universe might not have existed. There would be no atoms, no energy, no space, no time, just nothing. But here we are. There is something. Why? Some philosophers say nothingness is unstable. Absolute nothingness would allow quantum fluctuations, because even the rule of no thing would itself be something. And once the fluctuation begins, universe is formed. But this is not satisfying, because an environment where laws that allow quantum fluctuations exist is not nothingness. There is something there, the laws. Another approach, necessity. Maybe the universe is logically necessary. Its non-existence would create a logical contradiction. But how could that be? In modal logic, a necessary thing is true in all possible worlds. A possible thing is true in at least one world. So is the existence of the universe necessary or merely possible? Most philosophers say it is possible, meaning the universe might not have existed. But then, why does it exist? One answer, self-causation, causa sui. The universe contains its own cause. Spinoza defended this idea. But how would that work? How can something exist before itself and create itself? Quantum mechanics offers an interesting possibility. Closed time-like curves, loops that go backward in time. If such loops are possible, the universe may have created itself in a temporal sense. A future event creates its cause in the past. But this is still not satisfying. Where does the loop itself come from? Maybe the answer is this. The question why is only meaningful inside the universe. For the universe itself, there is no why. The universe is a brute fact, a fundamental reality that requires no explanation. To some, this feels like an intellectual defeat. Saying it just is feels like giving up on the mystery. But think about it. Every chain of explanations must end somewhere. You can go back infinitely, but that is not an answer either. Infinite regression. At some point, you must accept something unexplained. Maybe the universe is that unexplained thing, the most fundamental level. And accepting this is not defeat, but understanding the depth of reality. Now, let's face a difficult reality. Maybe we will never know what came before the Big Bang. Science is built on observation and experiment, but we cannot directly observe the time before the Big Bang. Light cannot reach us from that era because space was opaque. The cosmic microwave background radiation comes from 380,000 years later. Before that, the universe was not transparent to photons. And the Big Bang itself, the singularity. There, mathematics breaks down. General relativity exceeds its limits. Infinities appear. Some physicists say, this is the boundary of knowledge. We can never know beyond the singularity, not just in practice, but in principle. Logically, we cannot know. Penrose's cosmic censorship hypothesis says singularities are always hidden behind event horizons. The universe does not allow naked singularities. Maybe this is a mechanism to protect information. At the singularity, information is destroyed, but the event horizon isolates this from the rest of the universe. If the Big Bang is a singularity and singularities are regions of ignorance, then in principle, no knowledge can be gained about the before. But maybe the singularity is not real. Maybe quantum gravity eliminates it. Then information could be obtained, at least in theory. Still, there are practical difficulties. Testing quantum gravity at Planck energy is far beyond our current technology. Planck energy is 10 to the 16 times higher than the energies at the LHC. Building such a particle accelerator would be the size of a galaxy. We can look for indirect evidence. Patterns in the cosmic microwave background, primordial gravitational waves, might provide clues. Gravitational wave detectors like LIGO and Virgo might detect gravitational waves left over from the Big Bang, a stochastic background. But this is a very weak signal. The James Webb Space Telescope and future telescopes will observe the universe's first stars, the first galaxies. Maybe there are clues there about the mechanics of the Big Bang. But we cannot directly see the before. We can only make indirect inferences. Is this the limit of science, or just the limit of current science? History has taught us that saying we will never know is dangerous. In the 19th century, they thought we would never learn the composition of the stars. They were too far away. Then spectroscopy was developed. At the beginning of the 20th century, they thought we would never see inside the atom. Then quantum mechanics was developed. Maybe in the 22nd century, understanding what came before the Big Bang will be simple. Maybe children in school will learn it and wonder, how did the old humans not know this? Or maybe we really will never know. Maybe some questions must remain unanswered. And that too is an answer, one that teaches humility. Different theories about what came before the Big Bang lead to different philosophical conclusions. If cyclic cosmology is correct, if the universe goes through infinite cycles, then there is no first cause. Everything comes from something before it, an infinite chain. This resonates with the concepts of endless cycles in ancient Eastern philosophies. Samsara, the cycle of birth, death, and rebirth, not just on the individual level, but on the cosmic level. This perspective could lead to nihilism. If everything repeats, does anything have lasting meaning? But you could also think the opposite. Every moment is valuable because it will repeat forever. Nietzsche's idea of the eternal return. If the multiverse hypothesis is correct, if there are infinite universes, then our universe has no special importance, just one of infinite possibilities. This teaches humility in terms of scale, but at the same time, it means each universe is real in its own way. Our experience is not lost in infinity. If the simulation hypothesis is correct, then the concept of reality changes, but maybe that is not so important. Even if simulated, pain is real, love is real, beauty is real, experience is real. If the universe emerged from a quantum fluctuation, from nothing, then it is not a miracle, just statistics. But does that reduce the miracle or multiply it? Something emerging from nothing, simply because quantum laws exist. Perhaps that is even more astonishing. If the universe is mathematics, Tegmark's hypothesis, then existence is platonic, ideal, abstract, timeless. But we are conscious substructures inside that mathematical structure. Mathematics is experiencing itself. Each scenario presents the meaning of existence in a different framework, but they all share a common theme. The universe is understandable. It follows laws. And we may be the way the universe understands itself. Carl Sagan once said, "We are a way for the universe to know itself." This is a profound idea. Billions of years of cosmic evolution eventually led to consciousness, and now that consciousness questions its own origin. Maybe the meaning of existence is this: to understand, to be curious, to ask, to search. Even if we never find the answers, to keep asking the questions. Even if we never fully understand what came before the Big Bang, asking the question itself is one of the things that makes us human. Curiosity, the desire to explore, and fearlessness in the face of the unknown. The question of what came before the Big Bang is not only scientific. For thousands of years, different cultures and religions have given their own answers to this question. In many creation myths, the universe is created from nothing, the ex nihilo creation. In Christianity, God creates the universe with His Word, first nothingness, then existence. In Islamic cosmology, it is similar. Allah says, "Be," and it is. Time, space, matter all begin with God's will. In Jewish mysticism, Kabbalah offers a more complex model. Tzimtzum, God's self-contraction. The infinite divine light withdraws itself to make space. In that void, the universe is created. The reduction of God's presence makes the universe's existence possible. In Hinduism, we see cyclical cosmology. Brahma is the creator of the universe, Vishnu the preserver, Shiva the destroyer, and the cycle begins again. The idea of day and night. A day of Brahma lasts 4.32 billion years. Then comes night, and the universe dissolves. Then a new day, a new universe. This is surprisingly similar to modern cyclical cosmology theories. Ancient Indian philosophers spoke of timescales of billions of years, scales that were unimaginable in the West until recently. In Buddhism, the concepts of beginning and end are illusions. Samsara, the cycle of existence, is beginningless and endless. Even asking the question is wrong, because the idea of linear time is a misconception. In Taoism, the Tao, the way, exists before everything. It cannot be defined, it cannot be named. The Tao that can be named is not the eternal Tao. The universe emerges from the Tao, but the Tao exists outside time. In some Native American cosmologies, the universe is created in dream time. Time is not linear, but spiral. Past, present, and future are intertwined. Modern science seems different from these myths, but some similarities are striking. Cyclic models, the holographic principle, quantum uncertainty. Some ancient ideas seem to be returning in new scientific forms. Of course, modern science is based on experiments, myths are not. But myths are ways the human mind relates to the universe, and perhaps that relationship is not only cultural, but also based on deep intuition. Einstein once said, "Science without religion is lame. Religion without science is blind." Perhaps true understanding lies in their synthesis. Science answers the how questions. Religion and philosophy answer the why questions. In the coming years and decades, we may learn more about what came before the Big Bang. But how? The first path, better telescopes. The James Webb Space Telescope has already started to see the earliest galaxies in the universe. Future telescopes will go even further back. Maybe we will see the explosions of the first stars. Maybe we will detect indirect signals from the pre-photon era of the universe. The second path, gravitational wave detectors. LIGO and Virgo have detected black hole and neutron star collisions. Future detectors, the space-based detector LISA, may catch weaker signals. Maybe we will detect the primordial gravitational waves left from the Big Bang. This could confirm the theory of inflation, and maybe give clues about what came before. The third path, particle accelerators. The LHC found the Higgs boson. Future accelerators will reach higher energies. Maybe they will find supersymmetric particles, maybe extra dimensions, maybe hints of quantum gravity. The fourth path, quantum computers. Some problems are too complex to solve with classical computers, like quantum gravity simulations. But quantum computers may handle these simulations. Maybe we can simulate the first moments of the Big Bang, maybe even what came before. The fifth path, more detailed analyses of the cosmic microwave background. The Planck satellite collected amazing data. Future satellite missions will map it in greater detail. Polarization patterns may be the signatures of primordial gravitational waves. The sixth path, neutrino observatories. Neutrinos are particles that interact with almost nothing, but that makes them cosmic messengers. If we can detect neutrinos from the very early universe, we could get information earlier than photons. The seventh path, theoretical breakthroughs. Maybe we will finally understand quantum gravity. Maybe string theory will become testable. Maybe a completely new theory will emerge. But the most important path, thinking differently. History has shown us that major breakthroughs usually come from paradigm shifts. Einstein thought about space and time in a new way. Heisenberg and Schrödinger embraced uncertainty. Maybe to understand what came before the Big Bang, we must completely rethink the concept of before. Maybe the problem is not that we can't find the right answer, but that we are asking the wrong question. Maybe instead of asking what was before the Big Bang, we should ask a different question. But which question? We don't know that yet. And maybe that is the most important thing left to discover. And here we are. We have seen magnificent theories about what came before the Big Bang: cyclical universes, multiverses, quantum bounces, holographic principles, simulations. Each one fascinating, each one speculative. The truth is, we don't know yet, and maybe we will never know. But this is not a failure. Science advances not with answers, but with questions. Every answer brings new questions. This is a journey with no end, and maybe it shouldn't have one. The question of what came before the Big Bang teaches us a deep lesson. The universe is stranger than we imagined. Every discovery reveals more mystery. The universe is like an infinite onion. Beneath every layer, there is another layer. And that is beautiful, because curiosity is the essence of the human experience. If we knew everything, what would we do? There would be nothing left to be curious about, no new place to explore. For now, what came before the Big Bang remains a mystery. But this mystery does not make us smaller. On the contrary, it makes us greater, because we can ask such deep questions. We can question the origin of the universe. We can reconstruct a 13.8 billion year story. And who knows, maybe a century from now, this text will seem archaic. Wow, back then they didn't know. Maybe our grandchildren will read about what came before the Big Bang in textbooks. Maybe for them, this question will be as simple as, why is the sky blue? Or maybe the mystery will remain. And that is okay too, because mystery is one of the things that makes life worth living. Thank you for taking this journey with us. We couldn't show what came before the Big Bang because no one knows yet. But we hope we could show how deep, how fascinating, and how important this question is. And maybe the most important message is this: keep asking questions. Never stop being curious, because curiosity is one of the things that makes us human, and the universe is vast, mysterious, and magnificent enough to meet our curiosity. What happened before the Big Bang? We don't know yet, but we will keep searching, because searching is as valuable as finding the answer, maybe even more valuable. And so, this cosmic detective story continues. The next chapter will be written by you, the new generation of scientists, philosophers, thinkers. Maybe one of you will lift this mysterious curtain. Until then, look up at the sky, at the stars, and remember, all of them came from that tremendous first moment, from the Big Bang. And maybe that is exactly why living is so exciting. Good night.